Hi dear students, welcome back to our channel and Vinay Kumar Basics of Physics. Dear students, in this video we are going to discuss about the how we can connect cells in a parallel combination and when the parallel combination of cells is preferable. So here you have to know about that in this video. What is meant by parallel combination of cells? When we are taken number of cells, in those cells all positive terminals are given to one point and all negatives are given to the another point. In between them we are giving some external resistance. Then that is called here parallel combination of cells. Very simple. In parallel combination, all positive plates of all the cells, all positive terminals of all the cells are given to one point and negatives are given to the another point. In between them what we are giving some external resistance, that should be what we call parallel combination of cells. Dear students, here this is the cell 1 and this is cell 2 and this is cell 3, like that. We have so many like that. So here that should be having some EMF epsilon 1 R1 internal resistance, epsilon 2 R2 and epsilon 3 R3. Now these are given to one point. So this is the point, that is clear. Here what you have to say, positive, negative, positive of the second cell, negative of the second cell, and positive of third cell, negative of third cell. So all positives are given to one point. I am saying that is P. Clear. Now all the negatives are given to the one more point. This is the one more point. Here we are giving again like this, again like this. Now this is the point, what it is, Q. We are taking three cells. In those epsilon 1, epsilon 2, epsilon 3 are the EMF of the cells and R1, R2, R3 are the internal resistance of the cells. In parallel combination, the positive terminals or positive poles are given to the one point and negative points are given to the another point. In between them we are giving some external resistance. We are giving some external resistance like this. So this is the external resistance. So now you have to say this is the parallel combination of cells. So in between 2 points what you are giving some external resistance. So dear students, when the parallel combination of cells is preferable, when the external resistance what we are given, the value of capital R must be less than the internal resistance of the combination of parallel combination of cells. When the external resistance is very less, then only the maximum current is passing through the parallel combination. That's why what you have to say, in any combination, if external resistance is less, then we can prefer parallel combination. If external resistance is more, we can prefer series combination of cells. I already uploaded one video for series combination of cells, that is available in the channel and I will give it in the description also. So this is simply about children parallel combination of cells. Now we have to prove it. What you have to prove it? When external resistance is less, then only parallel combination is preferable. What's the reason for that? Let's discuss. Dear students, let us assume that m number of cells, each of EMF epsilon and internal resistance R, they are connected in parallel as shown in figure. Already just now only we discussed how the connections are in parallel combination. Very simple children. Here we are taken what is m number of cells, each of EMF epsilon and total internal resistance R. Each of EMF epsilon internal resistance R are connected in parallel. So like this, Here first cell, second cell, third cell, and this is the mth cell. So all the positive plates of the cells are given to this point, and all the negative poles are given to this point. All the positive poles given to this point, all the negatives are given to this point. In between them, what we are giving? Some external resistance R. And here I is the amount of current. What is epsilon? EMF of each cell. What is small r? Internal resistance of each cell. Clear? And what is capital R? External resistance. What is I? Amount of current in the circuit. So dear students, here these are in parallel. These are in parallel. That's why here the total EMF in the circuit must be equals to the EMF across every cell. EMF across every cell. So EMF across every cell. That's why what you have to say, total EMF is equals to what, right? Epsilon. Total EMF is what? Epsilon, because EMF across every cell is what? Epsilon. Clear? In the same manner, all the cells are given in parallel. That's why in parallel combination, what do you know formula? 1 by Rp is equals to 1 by R1 plus 1 by R2 plus and so on 1 by Rm. Like that, here all are having same internal resistance. All are having same internal resistance. That's why here we will write 1 by Rp is equals to 1 by R plus 1 by R plus and so on 1 by R. That how many times? M times. Then what, right? 1 by Rp is equals to M by R. 1 by Rp is equals to M by R. From that what, right? Rp is equals to R by M. So this is what it is? Effective resistance of the combination. What it is? Effective resistance of the combination. What to write? Rp is equals to R by M, children. So in this case, according to Ohm's law, what do we write? I is equals to V. Look here, children, we need some space. That's why I'm erasing. Here, according to Ohm's law, what do we write? V is equals to IR. I is equals to what? V by R. By using that, we can write I is equals to total EMF. Total EMF by total resistance. What it is? Total resistance. So in this case, here I is equals to total EMF is what? Epsilon. And total resistance. So here the resistance of the combination is what? R by M. And extra resistance is what? Here simply here we are like this we are saying. So now here this is the circuit. I is equals to epsilon by, here what it is? R by M. R by M is the resistance of the combination. And what is our extra resistance? How these two are? These are in series. That's what, right? I is equals to epsilon by R plus R by M. So I is equals to epsilon by S. Then what, right? I is equals to M by M into epsilon by R plus R. Clear? This is the amount of current in the circuit. I is equals to M epsilon by R plus R, children. Clear? I is equals to M epsilon by R plus R. This is the amount of current in the parallel combination of the cells. So if you want to understand very clearly, simply I am drawing the effective combination of all these. I am showing here like this. So and there should be given to here external resistance. Clear, children? Here this is the capital R and this is what? Total EMF is epsilon and effective resistance is what? Rp. That Rp is equals to what? What we got? R by M. Then simply what we are writing? I is equals to M epsilon by R plus R. We are getting the current, amount of current in the combination. So what we taken, children? R is so less than small r. When external resistance is so less than the internal resistance, this is the condition, then only we can prefer parallel combination. Clear? When external resistance is so less than the internal resistance of the combination, then only what you have to say, we can prefer the parallel combination. Why? Because look here, I is equals to m epsilon by, we are neglecting the r. R is so less than the internal resistance. That's why what, right? Yes, I is equals to m into epsilon by r. I is equals to m into epsilon by r. So it means that, children, here I is equals to, we will write m into epsilon by r. I is equals to m into epsilon by r. This epsilon by r, what it is? This is the simply amount of current through the single cell. Amount of current through the single cell. So let's discuss here. Very simple. When we have only one cell in the combination, we will write. So only one cell. Clear? Only one cell in the combination. One cell in the combination. What right here? This is the S and external resistance. Now what we write? This is the epsilon and this is R. EMF is epsilon and resistance is R. Children, you can feel that both are similar, but here what it is? This is the effective of the all the cells. Clear? Effective resistance of the all the cells. And now here only we are having only one cell. That's EMF is what? Epsilon, and this is R. This is R. That why what, right? According to Ohm's law, total EMF by total resistance, R plus R. Capital R is the external resistance and small r is the internal resistance. Then what we get? I is equals to epsilon by R plus R. Then obviously here I is equals to epsilon by R we can write. Why? Because R is so less than small r. External resistance is so less than compared to the small r. So then what, right? I is equals to epsilon by R. So this is the amount of current in a single cell. That's why in this formula what we got in case of combination of the cells, I is equals to m into epsilon by R. That means when the external resistance is less than the internal resistance, what you have to say? The amount of current in the circuit must be m times of amount of current in the single cell. Amount of current in the single cell. So that's why we can use the parallel combination, or when we can use the parallel combination? Yes, when external resistance is so lesser than the internal resistance, then the amount of current is increased by the m times of amount of current through a single cell, children. So this is a very important topic you have to remember. Got it, children? So I hope you understand. If you can understand this one, like, share, comment the video and subscribe the channel. Thank you for watching.